Hello Year 12 Further Mathematicians. We're just going to start a new chapter in the Further Core Pure 1 book. Chapter 2 continues with complex numbers. Chapter 2 is called Argand diagrams, which is a way to display complex numbers. Argand diagrams were named after the mathematician John Argand, and pretty much the main objective today is to be able to show complex numbers on this Argand diagram. Now, firstly, before we think about displaying complex numbers, let me remind you about the real numbers. So the real numbers, when you were first taught about numbers back in primary school or even before that, you would have been taught about a number line and placing numbers on a number line, and you would have started off with just whole numbers. Maybe you would have started off with 0 in the middle, and you would have the numbers 1, 2, 3, etc. going to the right, and then eventually someone would have told you about negative numbers, and that would be -1, -2, -3, etc. going to the left, and then you would have been taught about fractions, and the fractions go in between the numbers, and then decimals fill the rest of the gaps, and then every single number could be placed on this real number line. So the problem with that is, as we encountered in chapter 1, there are certain equations where I can make up the equation and use just real numbers, so something like x squared plus 4 is equal to 0, but the answer to that equation doesn't belong on this real number line, and the answer to that is an imaginary number or a complex number. And an Argand diagram is a way to express complex numbers starting off with a real number line, but then drawing an imaginary number line perpendicular to it. Very similar to a coordinate grid. In fact, pretty much exactly the same as a coordinate grid. And the y-axis, if you like, is the imaginary number line. We just abbreviate this to the real axis and this to the imaginary axis. And then this entire grid is used to plot complex numbers effectively like you would plot coordinates. So because this is a 2D diagram, what that means is complex numbers are two-dimensional. They're a two-dimensional number. Okay, so they've got a real component and they've got an imaginary component. So if I came up with a complex number, something like z equals x plus iy, the real part is x, the imaginary part is y, and I effectively plot this like I could plot a coordinate. We kind of prefer, rather than a coordinate, like a single point, that we use vectors instead. So effectively I'm going to plot the vector xy. So I go x across, y up, and that there would be my complex number z, which is equal to x plus iy. And this is how we're going to plot complex numbers on this diagram from now on. And this particular diagram now, any equation, polynomial equation, so quadratics, cubics, quartics, etc., you can make up any of them, and I guarantee every single answer is something you could plot, you could point to on this two-dimensional grid. Okay, so all of the answers to polynomial equations can be pointed to on this grid, so there's no need to ever say no real answers, whatever, anymore. They do exist. Now this grid is called an Argand diagram, there's another name for it called the complex plane. The word plane in maths means effectively a flat, two-dimensional surface. Let's have a look at EG number 1. We've got two complex numbers, Z1 and Z2. 2 plus 5i, 4 plus 2i. We need to show this on a Argand diagram. So you would draw a very quick real axis. They kind of abbreviate that to real Z, so real complex number, and then imaginary complex number. It's just the abbreviation. The first one we have to show is Z1, which is 2 plus 5i. And yeah, you kind of want to think of it a little bit like coordinates, or maybe better to think of it as a vector, 2 across 5 up. So let's just say that's 2, let's just say that's 5. And we label this Z1. Then Z2 is 4 plus 2i. So just say that's 4. Just say that's 2. And then that would be Z2, which is 4 plus 2i. And then the last thing we have to do is work out Z1 plus Z2. And there's two ways to do this. The first way is to use chapter 1 stuff to add both vectors. So you'd get 6 plus 7i, and then just say that that is 6, say that that is 7, and then that there would be Z1 plus Z2. Or if I drew this perfectly to scale, then I can treat these as vectors and do vector addition, and Z1 plus Z2 would effectively be Z1 plus Z2. Those two vectors put top to tail, and that would be it. Okay, if I drew it perfectly to scale. Now that's pretty much it. So all you've really got to do today is use this diagram, and yeah, you can effectively treat stuff like a coordinate grid effectively with a real x-axis and an imaginary y-axis, but definitely use arrows to express the complex numbers. So view them as vectors rather than coordinates. Now, if you find page 19, I'd like you to do exercise 2a. And let's do the evens plus 9. So the evens and question 9. And that'll be it.